Welcome to a brand new deep dive. And for anyone joining us today, our mission is to conquer what looks, at least at first glance, like an incredibly intimidating stack of handwritten theoretical physics
Well,
notes.
yeah, very intimidating.
Right. I mean, the document is literally titled Parametric Amplification in Magnetized Piezoelectric Semiconducting Plasma.
That title alone is, it's dense enough to make anyone's eyes just completely glaze over. It sounds like a random assortment of sci-fi buzzwords.
It really does. But if you are listening to this right now, do not worry. We are not going to sit here and just read pages of algebra and partial derivatives to you.
No, definitely not.
We aren't hosting a math quiz here.
Today.
The goal today is to extract the incredibly fascinating story that is buried inside all these derivations. We're going to figure out how physicists manipulate light, sound, and, electrons inside solid materials.
Because the math we are looking at isn't just some abstract theory. These handwritten derivations are the exact blueprints for how modern technological components actually function. It is the literal language of physical reality being translated into actionable engineering.
Exactly. So imagine holding a small, solid, seemingly inert crystal in your hand. You shoot a wave of energy into it, like maybe a laser or a microwave.
Right.
Then, by applying a magnetic field and harnessing the invisible microscopic vibrations of the crystal itself, you somehow manage to amplify a completely separate signal.
Which is wild.
It sounds like magic. But what we have in front of us is the mathematical sheet music that proves this highly choreographed dance of energy actually works.
Yeah, and to understand how that amplification happens, we have to look at the environment where this microscopic dance takes place. The theoretical model defines the setting as a piezoelectric semiconductor.
Okay, so that first word, piezoelectric.
Yes, that is the physical foundation for literally everything that follows in these notes. In a piezoelectric material, mechanical stress and electrical charge are physically permanently linked.
So if you take the crystal lattice, which is just the rigid grid of atoms making up the solid, and you physically squish it or bend it, that deformation generates an electrical charge. It's the exact same physical mechanism inside those clicky grill lighters you use at a barbecue, right? You push the heavy button, tiny internal hammer strikes a piece of piezoelectric quartz. The mechanical stress creates a sudden electrical charge, and then boom, that spark ignites the gas.
That's a perfect example. And the thing is, that mechanical to electrical bridge runs in reverse, too. If you expose that exact same crystal to an electric field, it will physically change shape.
It actually flexes.
Right, it flexes. So our environment here is a responsive, flexible grid. But the second part of that definition we mentioned is semiconductor plasma. Now, when most people hear the word plasma, they automatically picture the surface of the sun or, glowing